Hi, my name is Maria Vincent. I am a graduate student with the Institute for Astronomy in Hawaii. I'd like to apologize for my croaky voice. I kind of lost my voice over the last 2 days and just recovering from it. So, in today's module, you're going to learn about two very important astronomy and scientific data analysis Python packages, which are probably going to be your best friends should you choose to pursue astronomy research. Let's start with Astropy. In the Astropy lesson, you're going to learn, well, what Astropy is, what are some of the sub packages you can use, and some examples of these sub packages that help you with defining quantities, planning observations, and finally, we'll end with some ways to input and output astronomy files. So let's start with what Astropy is. Astropy is a Python package that is very helpful in letting you do various tasks in astronomy and astrophysics. This includes, planning an observation, reducing some data you got from that observation, analyzing the data, and other numerical and modeling tasks that you would need in astronomy research. Now, how to install and import this? As you might know, pip is the best way to install most Python packages. So you can just use pip install Astropy from your terminal, and it should install the latest edition of Astropy. You could also install it using conda install Astropy. Now, if you download Anaconda and that's how you're using Python, it should already come with Anaconda because it is a widely used package. In that case, if you want to update it to the latest version, you just do conda update Astropy. And to include everything that requires Astropy to run, because Astropy is not a standalone package, it requires things like NumPy and Matplotlib and things like that for it to it kind of uses these things as crutches. You can use this command. And yes, once you've installed this, you can import Astropy as import Astropy. But Astropy is really big, so you'd rather just want to import specific sub packages. Most of Astropy's functionalities lie in these subpackages. You can import them in this format that I've shown from Astropy import subpackage or import astropy.subpackages s. Or if the subpackage is really large, which is the case for most Astropy subpackages, you would just import the very specific class of functions that you need as from astropy.subpackage import class. Right now, this might seem very abstract to you, so I will dive more into some detailed examples. So these are some very common Astropy subpackages: units, constants, and coordinates. I'll show you units and constants a little bit later. Coordinates is useful when you are talking about coordinates of various astronomical objects. For example, in astronomy, we use two coordinates, RA and dec, which is very similar, which is right ascension declination, very similar to latitude and longitude we use for maps. It is a latitude and longitude for a star. So instead of doing the math in your head to convert between more conventional units like altitude and azimuth, which is the position of a star with respect to your horizon, you would just call up astropy.coordinates and it will contain the things that you need to convert between common coordinate systems used in astronomy. We also have something called coordinated and affiliated packages in Astropy. These are whole other set of packages. They are not under Astropy, but coordinated packages are maintained by the same people who maintain Astropy. Now, these are the reason I mentioned these here is you would likely not just use Astropy alone. You would require these other packages to help you with various tasks. So, for example, you could use AstroQuery if you're trying to get information on a target directly from SIMBAD or from the archive for a telescope or an instrument. So instead of going to the website, you can just use AstroQuery from Python. CCD-proc is to do CCD data reduction. Utils is for photometry. Affiliated packages are other astronomy packages that are not maintained by Astropy, but you can use them with Astropy. AstroML is becoming increasingly common as a lot of people are using machine learning in astronomy. Astroplan is something that you could use to plan observations. Astropy is Astropy alone, and maybe with AstroQuery as well can help you with this, but Astroplan is also just another option if you'd like one. Dust extinction is particularly useful for those studying interstellar medium, galaxies, etc., to understand how less bright a target gets because of the dust, because of the extinction caused by the dust between you and the target. Now, as promised, let's get a little bit deeper into understanding units and constants, which are your quantities in Astropy. So astropy.units is very helpful when you're handling and calculating using different quantities with different units. Instead of having to, multiply by different factors to convert everything to the same unit, if you just multiply by the units, then Astropy knows how to handle that calculation. So for example, I want to calculate velocity. And for velocity, I have a distance in meter and time in second. And if I apply units this way, u dot meter, u dot second, the value should correctly give me what the velocity value is. And if you look up what q dot unit is, it will say meter per second. Parsec is a common measurement of distance and not time, as Star Wars tells you. It's a common measurement of distance in astronomy. So most of you might not know what parsec is. So let's see what a parsec is in kilometer, which is a more familiar unit. And to convert units, you just use .2 next to the variable that has the unit. So x is 1 parsec. So x.2 u.kilometer should convert parsec to kilometer, and this is what 1 parsec is in kilometers. Now that's units. But in astronomy, you also use constants. And instead of having to, copy paste the value of the constant each time, you just call up the constant from astropy.constants. So G is a very common, the universal gravitational constant is a common constant that you use. So instead of having to copy paste the value G, you can just use constants or C.G, and it should give you, and if you just print it, it would give you everything that you need in this gravitational constant. It will give you all the information you need. You just have to use C.G in all your calculations. This is a quick assignment I'd like you to do. Let me see. All right. Yes. I'm in the interest of time, I'm not giving you some time to work this out. I can show you how this works. So calculate the gravitational force between a 3 solar mass star, which is a star 3 times as heavy as ours, and its 10 Jupiter mass planet companion, 2 AU away, 2 astronomical units away. An astronomical unit is the distance between Earth and the Sun, so 2 times that is 2 AU. So it's a very simple calculation you can do. You can define the mass of the star using 3 times C dot mass of our sun. You can define the mass of the planet as 10 times mass of Jupiter, which is also a constant in Astropy. And you define the distance using Astropy units. And you can calculate the force using the gravitational constant and the variables you defined, and you should get this as your answer. Even though I've shown it worked out to you, I would highly recommend that you do this. In this presentation, anything that is marked with this green box that says assignment is something for you to do. In further slides, you will see things marked as assignments with no solution. That is for you to work out. Now, input and output. So in astronomy, when we observe and when we record data, we read and write this data in very different formats. Astropy.io is a unified interface that helps you do this. It helps you create a common pathway between importing and exporting data in different formats. So one example of this is astropy.table. .dat is a common format in which you store tables with astronomical information because it's very compact. So if you use astropy.table and from that you import table, you can use that to read these .dat files, and then you can use it to write it into a format you'd like. So here I'm importing some photometry data from photometry.dat, and then I'm writing it into a .text file. Now, a .text file is a file that you use in the language LaTeX. I kind of forget if you've done this module already. If not, it's a way for you to write scientific papers. And so instead of having to, write it manually by yourself, just using this will put the whole tabular information from .dat into text. FITS is another commonly used data format in astronomy. It's short for Flexible Image Transport System, and it is used to, transport, analyze, and archive scientific data files. It's more than just a regular image format because it also contains multi dimensions to it. It has an image dimension, which stores your image data, and it also stores other metadata, which is information about the data itself. So FITS files have two segments to them, header and data units, which is called HDU for short. The primary HDU, typically, which is a primary array, contains your actual data itself, which can be a 1D spectrum or a 2D image or a 3D data cube. A data cube is usually when you have different varieties of data for the same target. It could be, a visual image of the data and then a spectrum, or the visual image of the data in different wavelengths. So that is the primary HDU, which is the primary data. And then you have image extensions. The image extensions are usually other added information to it. And so the way to look at it is the header unit and the data unit. The header unit is the information that is recorded, let's say, by the instrument when taking your data. It tells you, what's your target, how big your data is, who took the data, how is it formatted, etc. And the data unit is what follows the header unit, and it contains the actual data itself. So this is something you can test very easily. Test0.fits is a default fits data that comes with your Astropy installation. So you can retrieve that data this way, and then you can do HDUL equal to fits.open and that image. You should be able to get, this is an exercise for you. You should be able to see what information you can retrieve from this. This is the only file that we need to import using fits.util.getTest data file path, because this is a file that resides in your Anaconda library, your Astropy installation. However, for most FITS files, you just need to do fits.open and the name of the file. If you directly just want to get the data, you can use fits.getData. If you directly want just the header, you can use fits.getHeader. Using HDUL is more convenient because then it imports the data and the header at the same time. Now, how to plan an observation. Now, to plan an observation, you need to take into account several things. Of course, you need to take into account what target you're observing. You need to take into account the date and time and the location of when you're observing, because depending on that, the position of the target on the sky with respect to your telescope is going to change. And then you need to also take into account the location of the moon. If you're observing in visible wavelengths, then moonlight can overshine your target if it's too close to the moon. But if you're observing in infrared or radio, this doesn't matter. So here is a short assignment I have for you. You have to plan an observation of Fomalhaut, which is a very bright star, using the Subaru telescope. You have to, so for this, you need to do several things. You need to generate the coordinates of the star and the observing site. This is how you start, and then you can plan the observation. I will post a solution to this because this is a bit of a complicated tool, but the reason I gave this as an exercise is so that you can explore how these packages work in your spare time and figure out what you need to do. And there are worked out tutorials and examples you can find online. And while I did show you how to install Astropy, and Astropy does come with your Anaconda installation, Astroplan doesn't. So you can use pip install Astroplan to do this. And an optional assignment, in case you finish the first one and you have plenty of time left, there are other tools you will need, like astropy.time and astropy.visualization, to help you plot and see where, where on the night sky your target is. Yeah, the only reason I omitted it is that we have more time to discuss Scipy as well. These are some references I would recommend for Astropy, especially because it's a very new package and very different from things that you would commonly use like NumPy or Matplotlib, which you'll see next week. Now, moving forward to Scipy, we're going to look at what Scipy is. Again, look at some units, quantities, and constants, and follow an optimizer and interpolate. Follow what an optimizer is, what interpolation is like, and I will pause for some Q&A. I won't be there to answer those questions, but you could probably ask Faye. So what is Scipy? It is a very fundamental package for data analysis, for any type of scientific analysis, really. This has been commonly used across various fields, and it comes packaged with several tools for various algorithms, like for optimization, interpolation, for statistics, for matrix multiplication, manipulation, etc. So the same routine, how to install this. Pip install Scipy, it's standard. Whoops. Or you can use Conda. Conda install Scipy or Conda update Scipy since it already comes with Anaconda. Now to look at the quantities. So Scipy also has a concept for constants, which you import the same way as you did for Astropy. These don't contain astronomical constants, but it does contain a set of built-in scientific constants and unit factors. You don't have a separate thing called units over here. It's all packaged into constants. So for example, you want to use pi, but you don't want to repeatedly import it. Just import scipy constants, and if you print c.pi here, you will get the value of pi. Now, anytime you want to see what information is contained within a variable, just use dir and put the variable in parentheses. That should give you all the information there is to the variable. In this case, the variable is c, which is what we're calling our constant subpackage. So this should allow you to see what constants Scipy has saved for you. And as you can see, it's a lot. You have your standard constants like the Avogadro's number, Boltzmann constant, G from before, Planck's constant, Stefan-Boltzmann constant, which you use, for luminosity and temperature calculations. You have the same thing as parsec. And then you notice you also see some units. We can talk about it a little bit more. So these all constants in Scipy they belong to one of these categories. I won't be going into these in detail, but I can show you two in specific. Metric is your everything that follows your SI units. So under metric, you get kilo, centi, micro. Basically, these give you the multiplicative factor with respect to meter. So kilo is 1,000 because it's 1,000 times a meter. Centi is 0.01, which is 1/100th of a meter. Micro is 1/1,000,000th of a meter, which is micron, which is very commonly used in science. Similarly, if you were to look at what's under angle, you have the multiplicative factor or the conversion factor with respect to radian. Radian is a standard unit for an angle, but a lot of us use degrees, arc minutes, or arc seconds. And so if you use c.degree, c.arcmin, or c.arcminute, or c.arcsec, or c.arcsecond, these are the values you'll get. I would encourage you to explore everything that comes under it. Now let's look at optimizers, which is a very helpful tool in Scipy. Optimizers basically contain a set of functions and procedures that help you optimize a function or an equation. And what do I mean by optimize? It can mean several things. It can help you. It can mean to find the root of an equation. It can be to find the maxima or the minima of a function, or it can be to fit an equation or fit a curve. So if you want to find the roots of an equation, let's define this equation, x plus cosine of x. You get cosine from numpy. And I want to find what the root of the equation is, which is what x is. So if I use, root equation 0, my root contains a lot of information. It contains information on the function, the method used to find the root, and the root value itself. So if you just want the value, use my root.x, and you should get this. Now, minimize will help you find the minimum of an equation. I have this quadratic equation here, x squared plus x plus 2. And if I use minimize on it and find what the minimum is, I should get this value. Now, the reason I use mymin.x and not just mymin is because if I use mymin, I'll get a whole bunch of information. What other information is stored in this? You can just print mymin and check that out. Now, curve fit. Curve fit, as I mentioned earlier, is to fit a curve. For that, you need an equation, which is your curve. You need the x data. You need the y data as well, because that's the so because with the y data, then curve, because what the way curve fit does, it optimizes the not necessarily variables. So let me actually go through this example. That way it would be easier to understand. So I have a very simple standard linear equation here, mx plus c. And I already have some predefined x data, 0, 10, 50. Now, m and c is 2.5 and 5.0 here. And let's generate a sample y data, which is, which is just, which is x, m, and c in equation. And I'm going to add some random noise so that it's not just, it's not fit within the equation itself. Now, my goal here is to fit this weird line that I have. I know what the equation is. I know what my x and y data are. Now I need to find the right values for m and c so that my equation with this x can give me what y is. Does that make sense? I hope that makes sense. It is a little complicated to understand, but let's go further and then hopefully you can make sense of it. You can use curve fit to fit. So basically, you're trying to find the best possible values in m and c to make sure that this y data, which is noisy, because I've added np.random.normal, the noisy y data is fitted to this equation. So curve fit gives you two outputs. It gives you p-opt, which is your optimized parameters. In this case, the parameters we are optimizing for are m and c. And p-cov is a covariance matrix, which you can use to find the uncertainties in your new y data. So m-fit and c-fit, you can get it as p-opt 0 and p-opt 1. Now, I know you haven't done matplotlib, but the only way to really understand whether or not this worked is to actually plot it and check it out. So if you plot x data versus y data, you should get, so for this, you need to plot your original x data and y data. And then you need to plot x data versus now whatever you get out of the equation using m-fit and c-fit. And this is what you should get. The noisy data might look certainly a little different because I used np.random. But basically what it does is, so you can see now, m and c is not 2.5 or 5.0 anymore. It's a little less than that because it's basically altering my equation. It is adjusting my equation, or I guess finding the right m and c value so that I'm as close of a fit to this noisy data. And the one comment you'd have noticed is a curve fit also takes an additional parameter called guesses. You can enter your guesses for m and c. Here it doesn't matter so much because it's a very simple equation, but for something more complicated, your guess of m and c can make a huge difference. Finally, let's talk about interpolation. Interpolation is basically a method for generating points between two given points or between multiple given points. It is useful when you have a non-continuous data set and you want to make it more continuous. There are several data sets and several ways to interpolate for those data sets. Here I'm showing an example of interpolating a data set with one variable. So imagine you have this x data 1, 2, 3, 4, and y data that's also, my y data is definitely not 1, 2, 3, 4. I am sorry. Or maybe it is. Just give me a second. I will figure this out real quick. Sorry about that. So this is my X and Y data. And now I want to interpolate such that I can make this a slightly more continuous data set. So for that, I use interpolate. Okay, there is another slight mistake. So I imported as from scipy.interpolate import interp1d. So interpolate.interp1d won't work. I just need interp1d. Let me see if I can quickly annotate this on here. Yeah. Yeah, I don't need this. I just need interp1d because as you can see, I import the class interp1d from scipy.interpolate. So interp1d, x data, y data will create this sort of wonky function. And let's say I defined a new array of x that has values between these, as you can clearly see. So if you put this x into f interp, it should give me y that is interpolated based on x and y. It's making its best guess as to what this function is based on the based on the shape of x and y. This will make more sense if you plot it. And when you plot it, when you plot it, this is what you see. In blue is the original data. Let me erase this real quick. And red is what I've interpolated. This is Python's best guess as to what the interpolated data should look like. Now, I'm not saying that this is a perfect solution, and this is perhaps not the best example because I don't have enough data points. But when you have a lot of data points and you clearly notice sparseness and you want a more continuous way of looking at it, this is a good option. And this is for 1D. Interpolate also makes a lot more sense actually when you do it over a 2D data set. Due to lack of time, I will leave that as an exercise to you. So the exercise is to try 2D interpolation. I would highly recommend using Scipy tutorials interpolate as a starting point because it clearly walks you through steps and shows you how interpolation can make a difference. Rectangular grid interpolator, rect bivariate spline are two basic 2D interpolators. You might think, oh, if there's interp1d, interp2d should exist. Interp2d exists on the older version of Scipy, and it has been depreciated now. And in the future versions, it would be removed. So it'd be best for you not to use it since you're going to lose access to it eventually. So that's all I have. I do hope that you learned the existence of Astropy and Scipy and how these tools are super helpful for you in astronomy and for data analysis. This is a time for you to ask any questions. You can reach out to me on Discord through the mentors channel, and I will be available to answer any questions, or you can direct any questions you have to the mentors who are currently online, and I'm sure they'll be able to help you. Thank you.